So hello everyone, welcome to the channel. So in this video I'm gonna show you mapping annual frost days from 1979 to 2020 using ERA5 daily data in Google Earth Engine. So now let's get started. So mapping annual frost days using ERA5 daily data in Google Earth Engine. So first let me explain about what is a frost day. So the frost day are the days when the minimum air temperature drops below 0 degrees Celsius, leading to the formation of frost on surfaces. They are a key metric in climatology and often analyzed to understand the frequency, how often the frost occurs in a given period, and duration, the length of the frost period, and intensity, how far the temperature falls below the freezing. So the frost occurs due to the radiational cooling. The clear nighttime sky allows the heat to escape and cooling the ground and air near the surface. And the second reason is while the frost occurs is due to the cold air advection. So the movement of cold air masses from polar or the high altitude regions. And third is the topographic effects. The valley and low-lying areas traps the cold air and increasing the frost risk. So the frost days defined as the days when the minimum air temperature falls below 0 degrees Celsius and plays a crucial role in climate studies, agriculture and ecosystem dynamics. Understanding their spatial and temporal distribution helps to assess the climate variability, predict the extreme weather impact and inform the frost sensitive crop management. The traditional methods of frost day estimation relies on ground-based weather stations, which often suffers from a spare coverage, especially in remote regions like Norway. And the satellite and the reanalysis datasets such as ERA5 daily temperature data provides a high-resolution global consistent alternative for long-term climate monitoring. So this study we're gonna use Earth Engine platform to automate our to compute annual frost days across Norway from 1979 to 2020. So these are the methodology we're gonna adopt. So first we're gonna acquire the data, that is data acquisition, extracting the ERA5 minimum 2-meter air temperature data, and next is the temperature conversion. So transforming the Kelvin to Celsius and identifying the frost days. And the third step is to spatial analysis. So we're going to aggregate the frost days at the national scale and the temporal trends. We're going to visualize changes over the 4 decadals using time series chart. And last, we're going to export this particular output to our Google Drive. So in this analysis, we're going to estimate the number of frost days, the days where the minimum air temperature is less than 0 degrees Celsius. For example, over Norway using ERA5 daily temperature data from 1980s to 2020. So first we're going to define our region of interest. So to define our region of interest, let me navigate to my study region. So my study region lies here, so in Norway here. So now I have placed a point using this particular tool here called add a marker. So once you click this and drop a marker over your study region, for example, over the Norway, my region of interest. So once you did that, in the top section we have this new variable called geometry, points with containing the latitude and longitude. So we're going to click this option, and in that you're going to able to see we have this latitude and longitude of the studied region. So we're going to copy this using Ctrl+C in my keyboard, and I'm going to paste it inside this variable. So likewise you can define any study region of your choice here. So I'm going to paste my latitude and longitude over in this particular variable using Ctrl+V in my keyboard. So once you pasted your latitude and longitude, next we're going to load our country's boundary layer. So based on using this point using this point, we're going to filter our region of interest, that is our Norway, using this particular dataset called so that is the FAO country's boundary layer. So let me show you that this particular dataset. So this is a global administrative unit layer 2015. So the second level administrative unit. So the dataset availability is from 2014 to 2014. And using this particular code you can access this dataset here. So this particular data is a global administrative unit layer, compiles and disseminates the best available information on administrative units for all countries in the world, providing a contribution to the standardization of spatial dataset representing the administrative units. So you can go through the details about this particular dataset here. So I'm going to navigate to Earth Engine tab. So here I'm going to define a variable called global admin boundary equals to earthengine.featureCollection FAO simplified 500 meter 2015 level 0. And to add this layer, we're going to define map.addLayer global admin boundary referring to this particular variable. and we're going to set the default visualization parameter to this layer, and we're going to output the layer name as admin boundary. So now we're going to run this code and let us visualize the result. So now we are currently visualizing the global admin boundary layer, so you can able to see that. So to select this particular region of interest, that is Norway, I'm going to filter this particular study area called Norway. So for that we have placed this point over this particular study area. So using this point, we're going to filter this particular admin boundary, that is our Norway. So to do that, in the next step, we're going to filter it based using the point data, and we're going to filter out the Norway out from this admin boundary. So to do that, we're going to define another variable called Norway boundary equals to Earth Engine dot feature collection FAO simplified 500 meter 2015 level 0, and dot filter. We can apply the filter function using our location point variable, which referring to this particular variable location point, which containing the latitude and longitude of the point data. And using that, we're going to filter the admin boundary called Norway. So for that, we're going to specify dot filter bound location point, and in the next step we're going to center this particular layer. So to do that, we're going to define map.center object Norway boundary with a specific with a suitable zoom level of 5, and to add this layer, we're going to define map.add layer Norway boundary, and the visualization parameter I'm going to mention the color as blue, and we're going to output the layer name as Norway boundary. So now let us navigate to the layer section here. So I'm going to turn this off and I'm going to turn this on. Layer called Norway boundary. So now here you can able to visualize we have managed to filter out the Norway boundary from our country's boundary layer using a point data, this particular marker. So in the next step, we have to fix up a period of our analysis. So the date of our start of our analysis and to the end of the end date of our analysis. So to fix that, to calculate the frost days for the specific year, for example, we're going to define an area of interest. For example, I'm going to define a variable called year start equals to Earth Engine dot date 2018 January 1, and we're going to fix the end period of our analysis, that is variable year end equals to Earth Engine dot date 2019 January 1. So the analysis will be starting from 2018 January 1 to 2019 January 1. So in the next step, we're going to load a ERA5 minimum 2 meter air temperature, and we're going to filter it based on the date we have fixed it here earlier. So let me explain about this particular dataset here. So ERA5 daily aggregates the latest climate reanalysis produced by ECMWF Copernicus Climate Change Services, and the dataset availability is from 1979 to 2020, and the dataset provider is Copernicus Climate Change Service. And using this particular code, you can access this dataset here. And ERA5 is a 5th generation ECMWF atmospheric reanalysis of global climate. The reanalysis combines the model data with observations from across the world into a globally complete and consistent dataset. So ERA5 replaces its predecessor. So ERA5 daily provides an aggregated value for each day for 7 ERA5 climate reanalysis parameter. So the 2 meter air temperature and 2 meter dew point temperature, total precipitation, mean sea level, pressure and surface pressure. Likewise, there is a lot of data has been available in this dataset. So now we're going to navigate to this option called bands section here. So the resolution of this particular band is around 27,000 meters is the resolution of this particular dataset. So it is a global level dataset, and these are the following bands that is available in this dataset, starting with the mean 2 meter air temperature. So it's in Kelvin, and the description is an average air temperature at 2 meter height, and the minimum 2 meter air temperature. It is a minimum air temperature at 2 meter height, and the maximum 2 meter air temperature is the maximum air temperature at 2 meter height. And we have a dew point 2 meter temperature band. So the dew point temperature at 2 meter height. And also we have this total precipitation band and surface pressure, mean sea level pressure. And the last two data is U component of wind and the V component of wind. So these are the following bands that is available in this dataset, and we're going to use this particular band called minimum 2 meter air temperature. So now let me get back to Earth Engine. So to load ERA5 dataset, we're going to define a variable called ERA 2018 equals to Earth Engine dot image collection EC MWF ERA5 daily, and in that we're going to select this specific band called minimum 2-meter air temperature band. So let me show you that. So we're going to select this particular band as this particular band called minimum 2-meter air temperature, and the minimum and maximum value. So this is the minimum air temperature at 2-meter height, and this is a daily dataset. And we're going to filter it based on specific time period. For example, we're going to filter dot filter date, year start and year end. So year start, which refers to this particular timeline 2018, and the year end, which refers to this particular date, that is 2019 January 1. And last, to visualize the details about this specific dataset, we're going to define print ERA 2018, and we're going to run this code. So in the console section, we have around 365 images available for this specific year, that is in 2018. So you can able to see the features here. So there is a lot of imagery that is available for the specific time period from 2018 January 1 to 2019 January 1. So a lot of imagery is available. So for example, I'm going to click this one of the image here. So we have the bands, the minimum 2-meter air temperature band, and properties. These are the following properties that is available, starting with the day and the month, and system asset size, and system footprint, system index, and system time indent, system time start, and the year. Let me minimize it. So in the next step, we're going to convert the Kelvin to Celsius and count the frost days based on the condition if the minimum temperature is less than 0 degrees Celsius. So based on this condition, so first we're going to convert from Kelvin to Celsius, and next we're going to count the total number of frost days based on this condition called if the minimum temperature is less than 0 degrees Celsius. So for that, we're going to create a variable called frost 2018 equals to ERA 2018, and we're going to create a loop function here, dot map function image, and we're going to mention return image dot now we are applying the condition. So we're going to subtract the Kelvin, that is we're going to subtract by the value of my 273.15 to convert to a Celsius, and we are applying a condition based if it is less than 0, it's going to return 1 if it is a frost, or 0 otherwise if it's not a frost. So for that, we are applying this condition dot less than 0, and last we're going to apply dot sum function. So in order to sum up all the frost days on the specific for example the particular year. So in the next step, we're going to add the frost days for 2018 to the map. So we're going to visualize the layer. So to do that, we're going to define map.addLayer frost 2018, and we're going to clip it based on our region of interest, that is Norway boundary. For that, we're applying the function dot clip function Norway boundary, and we're going to set the minimum and visualization parameter. So the minimum of 0 and a maximum value 115. The color palettes we're going to mention is white, blue, and dark blue, and we can add more colors in our layer section. So for now, we're going to specify white, blue, and dark blue, and we're going to output the layer name as frost days 2018. So now let us take a look at the layer here, layer section here. So we're going to turn off the admin global admin boundary layer. So we're going to specifically focus on the Norway boundary here. So now in the layer, I'm going to turn on this frost days 2018. So the layer is getting loaded up here. So now the layer, the frost days 2018 layers has been loaded up here, so you can able to see. So in that, we're going to click this option called the setting like symbol here, and it's going to open a new window called frost day visualization parameter. So I'm going to select the minimum as 2-meter air temperature band, and the custom section I'm going to select the stretch 90%. So once you applied it, so it's going to show you the range of value. So the range of value starts from 27.6 to 216.4. So this particular value which indicates the number of frost days. So the number of frost days which ranges from 27.6 days to 216 days. This 216 days of frost in the study region. So in that, we can apply some visualization parameter. For example, so this particular value ranges from white color, which indicates the lowest number of frost days, and the blue value which indicates the highest number of frost days. So for example, I'm going to change the value to a red color here. So I'm going to select the red color and click OK. So the red which indicates the highest number of the number of days in frost. So now we're going to click apply and visualize the result here. So the layer is getting loaded up here. So we're going to close this. So now I'm going to click the inspector tool here. So you can able to see the layer has been loaded up here. So I'm going to click this particular area and I'm going to use my inspector tool and I'm going to click this area here. So it's going to show the value, the number of frost days for the specific time period from frost days for 2018. So the number of days of frost in this study, in this point, is around 213 days of frost for this specific point in this study region for 2018. And similarly, I'm going to place my point inspector tool over this point area in the blue color. So you can able to see the number of frost days, which is around 132 days of frost. And followed by we're going to place the value here. I'm going to place it here. And now in this area, the number of frost days is around 63. So 63 days of frost for this specific study area, for the specific point in this year 2018. And also we can change the visualization parameter, the default visualization parameter, by removing this color sets here. And once you've remove those color, so it is currently in the default visualization parameter. So I'm going to run this code here. So the frost days 2018 layer is getting loaded up here. So you can able to see here the white color, which indicates the highest number of frost days, whereas the darker the black color, which indicates the lowest number of frost days for the specific study region in Norway. So for example, I'm going to use my inspector tool over this particular area here. Let me show you that. So I'm going to use my inspector tool over this particular area. You can able to see. So it's going to show us the frost days. So the number of frost days is around 78 for the specific study area. And I'm going to click this particular area here. So the number of frost days for this particular area is around 219 days of frost. Specific study, specific year in 2018 for Norway. So now using this inspector tool, you can able to see the number of frost days which is indicated. So the whiter area, which indicates the highest number of frost days, and the darker areas, which indicates the lowest number of frost days. So the next step to export this particular image to your Google Drive. So we're going to click this option. So we're going to click this option called we're going to enter as export.image.to-drive, and I'm going to mention image is frost 2018, which is referring to this particular variable frost 2018, and we're going to clip it based on our region of interest, that is our Norway boundary. So for that, we're going to clip Norway boundary, and we're going to export to our Google Drive. So make sure that you use this particular function float function, and the description I'm going to mention as frost days 2018 for Norway boundary, and the spatial resolution of this particular imagery is around 27,000 meters of resolution, and the region is Norway boundary dot geometry, and the coordinate reference system is EPSG4326, and the folder is the frost output. So now in the task section, I'm going to navigate to the task section here. You can able to see we have two different files here. So we're going to focus on this particular one, the frost days 2018 Norway boundary. So now to export this particular imagery to our Google Drive, we're going to click this option called run, and it's a new window pop up saying initiate image export. So the task is the frost days in 2018 Norway boundary. The coordinate reference system is EPSG4326, and the spatial resolution of this particular drive, and where we're going to export our dataset. So we're going to export to drive, and the file format is in GeoTIFF. And to click, make sure I click run to export this image to your Google Drive. So next, we're going to calculate the total number of frost days from the year 1979 to 2020. So to do that, we're going to define another variable called start year equals to earthengine.date. So we're going to mention the start year. So that is 1980 January 1, and the end year, I'm going to specify this variable using the variable end year equals to earthengine.date 2020 January 1. Now in the next step, I'm going to calculate the total number of years between these days, between this 1980 to 2020. So to calculate the total number of years between this particular time period, I'm going to use another variable, so called variable year count equals to end year dot difference start year and the unit in year, and we're going to use this function called to round up the number of years without any decimal places. We're going to use this particular function dot round function. So it's going to provide us the total number of years between these days from 1980 to 2020, which is around 40 years. So we're going to show you that. I'm going to navigate to the console section, and you can see from this console section, I'm going to run this. So in the console section, I can able to see the total number of years, which is around 40. So the next step, we're going to create a sequence of number from for a period of 40 years. For that, we're going to mention, we're going to create a variable called year list equals to earth engine dot list dot sequence. So starting from 0, so the year count dot subtract 1, and in that we're going to create a loop function dot map function I. So basically it's going to create a sequence of numbers starting from 0 to 39. That is from 0 years to 39, so which indicates a total of 40 years. And in the next step, we're going to return the image here. We're going to return start year dot advance earth engine dot number I, and the unit is in year. So basically what it's going to do is advancing by I year from for each element in the sequence. So basically it's going to return resulting in the list of 40 annual start dates from 1980 to and next sequence will be 1981 January 1, and the next sequence will be the 1982 January 1, and similarly up to 2019 January 1. So the sequence is going to start from 1980 January 1 to up to 2019 January 1. And last, we're going to, in order to visualize the total number of years for our analysis, which is going to be 40 years. So to confirm that, we're going to mention the print total number of years, year count. So year count, which referring to this particular variable here, so which going to indicates the total number of years, which is 40. And last is it's going to print a list of years. So it's basically it's going to print the list of years. For example, this particular one starting from 1980 January 1 to 2019 January 1. So now let us visualize it. I'm going to click this option called run, and in the console section you can able to see here the total number of years, which is 40, and the list of years. I'm going to click this arrow, so you can able to see the 0, which indicates 1980 January 1, and the value 1 here, which indicates 1981 January 1, and the value 2, which indicates 1982 January 1 up to 2019 January 1. So from 0 to 29, which is around 40 years. So in the next step, we're going to map over each year to compute the frost days. So basically we're going to map over each year to compute the total number of frost days for each year from 1980s to 2020. So to do that, we're going to define another variable called frost by year equals to earth engine dot image collection. So we're going to mention year list. So year list referring to this particular variable which holds the year list values. For example, this particular variable, so which is going to hold the values like this one. So from 1980s to January 1 to 2019 January 1. So we're going to use that and we're going to apply a map function here. So dot map function date. So it's going to take the list of annual start date created earlier and maps a processing function over each year. So the next step, we're going to create a variable called start. Variable start equals to earth engine dot date. So the variable start here, it's going to mention the January 1 of the year, that is 1980 January 1, and the variable end, we're going to define another variable called variable end equals to start dot advance by 1 year, unit is in year. So basically what it's going to do is January 1 of the next year will be 1981 January 1. So the next step, we're going to load our ERA5 dataset here. So for that, we're going to define a variable frost equals to earth engine dot image collection. So variable frost equals to earth engine dot image collection ECMWF ERA5 daily, and in that we're going to select the similar band, that is a minimum 2 meter air temperature band. To select this particular band, we're going to define dot select minimum 2 meter air temperature. And we're going to apply some filter function based on this particular set of timeline, that is variable start and variable end. So we're going to apply the filter that is dot filter date start and end, and in that we're going to apply a map function here, that is loop function dot map function img, and in that we're going to return the image dot subtract 273.15, so which going to convert the Kelvin to Celsius, and we're going to apply another condition called dot less than 0. We're going to create a condition called if the value is less than 0, so it's going to give a value of 1. So if the value is more than 0 degrees Celsius, so it's going to give the value as 0. So it's basically it's going to create a binary mask. And last is to sum this total number of frost days, we're going to use this statistical function that is dot sum function. So it's basically so it's going to sum all the frost days across the year, and last we're going to rename as frost days using dot rename frost days, and last we're going to return the frost dot set. So it's going to add the critical the important metadata properties to each annual result image, and in that we're going to specify system time start and start dot millisecond format. So it's going to give us in a millisecond. So the time series basically are using for timestamp for the time series start, and next is the system index, the start dot format in year, month and day. So the year identifier which is indicated in year, month and day. And next step we're going to create the time series chart for this analysis for the in order to visualize the total number of frost days for each year for the study area. So to create a time series chart for the frost days over the Norway, so we're gonna mention as print ui.chart.image.series, and the image collection we're gonna mention this frost by year, which is referring to this particular dataset here. So you can able to see frost by year. And next is we're gonna select the region, that is our study area boundary, that is Norway boundary, and we're gonna apply the statistical function called earthengine.reducer.mean function. So in order to acquire a mean number of frost days, so for that we are applying this particular statistical function earthengine.reducer.mean function, and we're going to mention the spatial resolution of this particular dataset, which is around 27,000 meters, and the X property is system time start, and you can add additional properties to this particular chart here using the dot set options. And the title we're going to mention average frost days in Norway from 1980s to 2020, and the h-axis are going to mention as year, and the v-axis are going to mention as frost days, and the line width and point size in the color. So now let us run this and visualize the result here. So we're going to visualize the time series chart for this particular study area, the total number of frost days for this study area. So from this result you can able to see here, so this particular is the title is average frost days in Norway from 1980 to 2020, and the frost days which is indicated here, and the year which is indicated in this axis, that is in unit year. And let us expand this graph here. So you can able to see here, so the highest number of frost days is observed in this year and during 1985, and the lowest number of frost days which is observed in 2019, which is during this particular year, that is January 2019. And also with this particular year, that is in during 2017, the lowest number of frost days which is around 173 days. And also this particular year, so by 2005 here, the frost days which is around 173 days of frost days in 2005 for the specific study region, that is Norway. And the highest was observed during in 1985, so the number of frost days was around 204. So from entire 365 days in a year, so around 204 days which is the frost day in this particular study area. And the lowest was observed during this particular year, so you can able to see in 2015, which is around 156 days of frost days. So let me get back to Earth Engine, and also let us visualize this particular result as the image here. So to do that, we're going to define this particular, that is we're going to visualize and export all year frost composite. So right from starting from 1980s to 2020. So to do that, we're going to define map.add layer frost by year, referring to this particular variable. So referring to this particular variable frost by year, and in that we're going to use this particular function called two bands function. And next we're going to clip it based on our region of interest using Norway boundary, that is .clip function Norway boundary. And the visualization we're going to set to default visualization parameter, and last we're going to output the layer name as frost days all year. So now let us take a look at this imagery here. So I'm going to navigate to the layer section, and I'm going to click this option called frost days all year. So the layer is getting loaded up here. So now here I'm going to navigate to the layer section here. So I'm going to click this layer called frost days all year. So I'm going to click this option here. So once you did that, a window pop-up saying visualization parameter. The frost stays all year visualization parameter. So now we're going to click to a single band grayscale, and I'm going to select the suitable year of my choice here. So we have the starting years 1980 up to we have 2019. So the start year of analysis will be 1980, and the end year of analysis will be 2019. So now I'm going to select 1980s, and I'm going to select the custom option here, and in that I'm going to select stretch 90%. So once you selected the stretch 90%, you can able to see here the total number of frost days, the minimum ranging from 29 days and to a maximum number of frost days, which is around 225 days. And now we're going to click apply. So the layer is getting loaded up here. So you can able to see here the layer is getting loaded. So I'm going to close this. So now the layers got loaded up here. So you can able to see from this image, so white area which indicates the highest number of frost days, whereas the darker areas which going to indicates the lowest number of frost days. So now again I'm going to use my inspector tool here. So I'm going to click this this particular area here. So now in the inspector tool I'm going to click this option here. So now here in the inspector section you can able to see here the frost days 2018. So the minimum 2 meter air temperature. So the number of frost days which is around 217 days of frost days for the specific area. So likewise you're going to click the coastal part of the study area. So I'm going to click here. So when the inspector tool you can able to see the total number of frost days which is around 23. So based on our analysis here, so you can able to see from this image, so towards the coastal part of the study area in Norway has the lowest number of frost days comparatively in the central and central part, and towards the eastern part of the study area has the highest number of frost days. So you can able to observe from this color here, so white area which indicates the highest number of frost days, comparatively the darker areas which indicates the lowest number of frost days, and the darker areas are situated towards the coastal part of this particular study area, you can able to see, which indicates the lowest number of frost days. So in the next step we're going to export this particular image to our drive here. So we're going to export this particular the frost days all year image to your Google Drive. We're going to mention export.image.drive, and image you're going to mention as frost by year equal dot to band function, and we're going to apply dot clip based on our study area boundary, that is Norway boundary. And to export as this image in the float, we're going to use the float data type. So we're going to mention dot to float function, and the description I'm going to specify as frost days 1980s to 2020 Norway boundary, and the spatial resolution of this particular imagery is 27,000, and the region is Norway boundary dot geometry function, and CRS, that is the coordinate reference system, is EPSG 4326, and the folder is frost output. So now we're going to navigate to the task section here, and we have this unsubmitted task called the frost days 1980 to 2020 Norway boundary. I'm going to click this option called run to now the new window pop up saying initiate image export. The task is frost days from 1980 to 2020 Norway boundary, and the coordinate reference system is EPSG 4326, and the spatial resolution is around 27,000, and we can export to our Google Drive, and the file name is frost days 1980 to 2020, and the file format is in GeoTIFF. So to export this image to your Google Drive, we have to click this option called run to export this image. And last, let us take a look at the application part of this particular analysis. So the application part of the study is first the climate change studies. So it tracks a shift in the frost frequency, aiding in the assessment of Arctic warming trends, and identifies the regions experiencing increasing and decreasing frost risk over time. And the second application is agricultural planning. So it helps the farmers to mitigate the frost damage to crops by identifying the high risk zones, and support decision making for the frost resistant crop selections. And the third application is ecological research. So assessing the impact on the boreal forest and tundra ecosystem sensitive to the freeze-thaw cycles, and correlate the frost patterns with the species migrations or the phenological changes. And the fourth application is the infrastructure resilience. So to inform the road maintenance and construction in the frost-prone areas, and predict the permafrost thaw risk in the northern Norway, and public health safety. So aligns the frost data with the ice-related hazards such as avalanche or a slippery road. So let me get back to Earth Engine. So in this video, I've shown you how to map an annual frost days from 1979 to 2020 using ERA5 daily data in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like.